instead, I'm Oliver Zeigermann, I'm DJ Korthose, and it's a little bit pointless. This is the link to the slides, but there is no slides. This is the slide. So this is a one-slide talk. And before you now leave, there's something else, and the something else is a notebook. So, oh, someone's leaving now because the one slide. Too bad. Close the doors now, so no one can escape anymore. So, okay, perfect. There is content, and the content is in form of a notebook. And this notebook is this one. If you know this link, you get to this slide, and then you click on this, and then you get to the notebook. And I tweeted this, and it might be interesting because the notebook actually is good. So the slide is not good, notebook good. So switch over to the notebook, and I think I just executed it, which was a good idea. And let's see what we have here. Has anyone ever seen this? Maybe I make it a bit bigger, still bigger. Is that good? Well, there's obviously no reason to sit in the back, but if you still do, I think you can read it. Has anyone any idea what this is and what it is running on? Just to make this a little bit more interactive, I mean, I don't know. What? Colab. That's Colab. And this is, well, I'm not associated to Google or anything like this, so, but I still like it a lot because it's a free notebook service. And it allows you to run your notebooks on the Google service, and it gives you a free high-end, well, it used to be high-end GPU. And this high-end GPU is, not sure if they show you the name here, but I know the name. The name is a K80, and the K80 used to cost around $10,000. So I'm not sure if it's still that expensive, but you can have it. And you can simply choose to use one of those GPUs, and recently they've added this thing here, which is a tensor processing unit. I'm not quite sure how it works, and I'm also not quite sure how a GPU works, but it's fast. And you get this for free. And I'm not quite sure why Google gives this to us, but you always have to log in, and then you, well, run it on their computer. So I probably wouldn't want to do it with data that is not meant to be seen by, well, Google. We sometimes say something like, Google can see it. I'm not quite sure what I mean by it, but I mean something, right? I mean, you mean something when we say Google knows our data, but I'm not quite sure what we mean. But if you don't want that, don't do it. So this is a notebook, and that means you have some text, this thing here, and you have some code, which is mixed in the text. And in this case, some of the cells have been hidden. This is some code here, and it's not interesting, but you get the point. So that means if you click on this thing, you get the very same thing, and you can execute things by pressing this run button, for example, and then you get the result, which is in this case very boring, but it could be interesting, and then it's cached inside the notebook. Before I keep talking about notebooks, who already knows what a notebook is? That's all, right? That's all of you. So I stopped boring you in this case. So what I have prepared, actually not for this talk because I didn't know I'm going to give this talk, but for something else, I prepared a data set, and this data set contains data about car insurance customers. And the data set has been downloaded. This is all boring. And this is, again, just boring code that loads in the data. And this, we could have a look at it if you had more time, but this is the first thing that's really interesting. Maybe you have to zoom out a little bit, how to make it fit. One more, no. Yeah, it fits. And this is a so-called pair plot. And this talk is not about a pair plot, but it's still an important first step to understand the data that we have. So we have three interesting, well, actually we have four columns. And as I said, this is about customers of an insurance company, and you have the age of the customers, you have the top speed of their cars, which is in, I guess it's in miles per hour, and then you also have like the miles they drive per year. And now, with a simple command, the command that's up there, it's not interesting how it looks like, you can plot each of these variables against another variable. And as we have three of them, we get 9 plots. Well, really? Yes. well, and the plots in the middle, they're a little bit special because this is miles on miles, so it shows something else. But this is typically the first step that you do. And you also see that there's a group, and the red group means that's a bad customer, green group, good customer, yellow group, somewhere in the middle. And you see, for example, you see something like speed against age, this thing here. If it was a little bit bigger, you would see it, but maybe you still do. There's this big red blob there. There's a green blob there. So this looks interesting. Surprisingly, miles per hour against top speed. Is there something funny?
It looks like a bad driver like maybe I'm sorry for interrupting.
No, it's great. I also want to find something like so. But you have a great point. Everyone can look at this and find something else. And then he said the worst drivers have the fastest cars. And let's see, maybe from. Oh yes, right. So that's quite funny because this plot here, again, this is not intended to be Bob plots like this, but this is like a distribution over the speed, and this is like the good drivers on average of cars that go 120 miles an hour, and the bad drivers, they peak here and they peak there. So if you have a fast car, you're likely to be a bad driver. If that was, well, if you read the data. And it's interesting, but you still see this data set is interesting, for one, and you still see probably the variables are pretty good. So typically in a data set you find a lot of strange variables that you don't want to use, but these are really good. So let's see. So we are doing supervised machine learning. That means from some of the variables you predict another. Which one would you predict? From which variables? Is it obvious? Is it? Just say it. So which one?
Pretty good.
Yes. That's what I want to do because my idea would be I have this data from my customers, existing customers. Now you apply or I apply for an insurance, and I want to predict from these things that I give and apply, I want to predict the group. But this is a deliberate choice. I could have predicted something else. I could have tried to predict the miles from the speed and the age. And I think this would have been really easy looking at this, because this is almost linear. So, surprisingly, there's a almost linear correlation between speed and miles. I had no idea, but this would be easier. Age against miles, hard, but this is not what we want to do. What's important here is that this is a deliberate choice. We choose to predict the group. So, now, that's what we do. This is just Python code that does this. It separates the stuff that we want to predict from the stuff that we use for prediction. And the code, it's far too long to look at it now. So what we do instead, so look at this plot. I think I still have to zoom out so you can see the plot. This is all the data, but in this case, to make it understandable for us, I restricted ourselves to 2 dimensions. We have 3 dimensions, but I will just use 2, which if this was like a real thing, I wouldn't do this. But I'm doing it now because in 2 dimensions, we still understand things. So I completely left out the miles. I just used the age and the speed. And this is just to give you an idea how the different machine learning algorithms work. There's no other reason. You would never do this in real life because you're losing a lot of information from the miles. But in this case, I think clearly see a lot of yellow ones here. The bad drivers have fast cars. There you go. Quite funny. Someone already said it in the saw it in the distribution.
Where did the name bad come from? Sorry,
I didn't. Oh, so red means it's a bad customer. That means from the customers that I have, I know they made a lot of accidents. And this is existing data. This is the data that I have. That's always the idea. You start from data that you have, and you have some, in this case, you have some labeling. You have some categories. And I just counted the number of accidents of these drivers, and there were quite a few. And that I mean, just looking at this, you could even see a lot. So it also looks like, unfortunately, almost starting from my age, your driving skills might be great. Maybe I'm not the oldest one here, but it's not clear. Some people are still good, and this is a very realistic data set because it's totally cluttered, it's totally mixed. It's not like one of those toy data sets where you have one group here and then one group here, and then you draw a line and then you're done. Because this is rarely the case in the real world, and would be totally boring as well. So now what we want to do, we want to teach a system how to, or put it the other way around, if you pick a random data point here that has been previously unknown, we want to teach a system that can make a prediction. Let's use me. I'm 47, my car used to have a speed of 100. I would be here. And now I want a system that makes a good prediction. Will I be a good driver or not? And what would you say, just based on the data? Good, right? And this could be something like a sanity check. You would say, okay, Ollie will probably be categorized as a good driver. I'm a very bad driver, but based on this data, it looks good for me. So that's our aim. We want to teach a system to make predictions for each of these spots. Okay, so the first trick that you have to apply, you may know already how it works, is that we split the data into training data we use to train the system, and then we save a certain percentage of the data for later to test how well we did. This is a little bit like faking unknown data, because what we really want to do is make predictions for data we don't know. So this is a typical split, 80% we use for training, 20% for testing. And that's important. So let's see. This is our training data, 80% of the data. It looks very similar to the thing before, but it's just 80%, random samples. And another 20%, far less as you can see, another set of random samples, but they're distinct. So 20% of the data up there, 20%, no, right. This is 20% of the data, the test data, and the other 80% we now use to train a machine learning model. And the first machine learning model we train is called K-nearest neighbor. Has anyone ever heard of this, K-nearest neighbor? So is it boring? Who would be bored if I explain? Who's too afraid to show their hands? You? That's just one hand. That means I'm going to show it. No, wrong. Oh, there. Too small again. And this is a visualization, and I always like that because it makes it easier to understand. And it's also linked from the notebook, so if you want to play with this later, do it. And this is a simulation of K-nearest neighbor, and it teaches us a lot. So these are the data points. You have 3 data points, or 3 types of data points. It's a little bit different than our example, but this is the best I could come up with. So you have the red, orange, and the green one. And now, the color of the background now shows the prediction of the trained machine learning model. So if the color of the background is red, like here, for this spot here, the machine learning model would predict red in this case. And if you look at it, it makes sense. And how does it do it? So it always takes a number, which is often called K, of nearest neighbors. That's why it's called K nearest neighbor. That's pretty simple. In our case, the number is it 2? No, it's 3. And it just counts the numbers of neighbors. This is the point that we're trying to predict for. It says 2 red ones, 1 blue one. We are going to predict red here. And now, if you change the number of neighbors to more, you see that the shape of the background changes. And the data set is really bad, so it's not changing for like the really good, but I think you can see in which way it changes. Look at this. Well, this is really crazy. Going up. You see how it changes? Maybe it's not great with this data set, but what do you see? You see a pattern? Well, what's the pattern? No, you don't see the pattern. Maybe it's not. You will see a better pattern in a minute, but maybe it's because the data set is mediocre. But what you should see is then when the k is really small, you should have like a really fragmented view. And if the k gets larger, you should see smoother boundaries between these areas here. But you're right, if you don't see it, I don't see it either in this example. But we will see it now in our notebook. So there's no time for the details and also not interesting, but now you understand how k-nearest neighbor works, sort of. I did this for our example. I think you can see it brilliantly here. So it only took, in this case, k is 1 nearest neighbor, and this is how this looks like. And now, how does it look like? Would you think that's good? No? No, you don't like it?
It has holes in it.
It has holes in it. There's strange holes. And this, I mean, these things are great for 2D. These are, well, typically you don't see the holes because it's so high dimension you don't see them. But you clearly see these holes here. And you see these spots. And this thing here is green because the nearest neighbor of this thing, well, of this area is just this spot. And now, this is the training data. This is the data that this thing has been trained on. So it perfectly, more or less perfectly, fits these data points here. It doesn't fit perfectly because at certain spots, there are 2 data points. You don't see them because they're directly over each other. That means at the points where you think the prediction doesn't make a lot of sense, it could be because there are 2 data points overlapping. For example, this one is green actually. It's hard to see, but it's green. So that's a bad result, but it's also pretty typical for k-nearest neighbor. Now, this is for the test data. Same background, different data. And now, this spot that I just showed you, the green one, now unfortunately there's a red one on it, because this is the data that simulates unknown data. And this means this is really bad, because we tried very hard to accurately reproduce all the training data, but for the test data, for the thing that's unknown, it totally sucks. So it's really bad. And you can express this in a number, and the number for this thing is around 60%, and that means 60% of the test data is predicted correctly. So that means if the prediction for this one, it's green, but it's actually yellow, so this is wrong, but this, for example, is right, and this and this. So 60% of these, this is correct. But when we look at the training data, there's also a percentage. In this case, we have 96% of them correct. And it could go up to 100. Because obviously, I mean, if you just take the next neighbor and this is exactly you, then you can be perfect. So, what do you do to make this better? So what we do now is that we find this effect, and this effect, does anyone know how this effect is called? Overfitting, right. That's overfitting. So we were overfitting, that means we were fitting to the training data, but not to the unknown general data. And the way to find overfitting, and I tried to show it in the visualization, but it worked, well, sort of, is to increase the number of neighbors. And we increased it to 39. I will tell you in a second how I came up with that number. But now you see these boundaries, there's still holes in it. And k-nearest neighbor is prone to overfitting. So it's very hard to get k-nearest neighbor to a very good value. And it's pretty bad in that case. But it's much better than before. You will see better ones, by the way. Need to check how much time I have. So I can, sorry, should have done this before. Oh no, that's good. Okay, it's all fine. Still 25 minutes ago, that's perfect. So we fought this overfitting a bit, And how did I come up with these values? And need to zoom in again. This is also a trick, which is called hyperparameter tuning. And it's very simple with a library that we're using for the k-nearest neighbor, which is called scikit-learn. And what you do, you say, make a grid search. That means like brute force search over all the possible parameters that I'm specifying. And then use all the CPUs that you might have. This works on CPU, not on GPU. And you give it a range for the neighbors from 1 to 50. And there's two ways of calculating the weights, like how much impact does a neighbor have. And it could be uniform, I think, which is the default. That means it doesn't matter. You just take the nearest neighbors. Or you can choose distance, which means the farther the point is away, the more weight it gets. And then you just search over all the parameters. And this takes 1.5 seconds, which is great for classic machine learning, because if you did this for neural networks, it would take minutes, maybe an hour, maybe longer. But this is just a second. So everyone is very excited about like deep learning these days. It's cool, it's great. But this stuff is also great because it's very fast and it's very simple to understand. And we still can explain. So if you make a prediction using k-nearest neighbor and someone challenges it and asks, well, why that prediction? You just look at the nearest neighbors and say, you are similar to these two customers and they were bad. So you can give explanations. And this is sometimes very important. At least in Germany, you are required by law to give explanations for certain choices that you make. And k-nearest neighbor is not the best strategy, but it's good at this. Give explanation. And you can understand, and you can explain it to almost everyone. So this is the result. So it goes over all the possibilities, checks the score of the test data, and sees where the score of the test data is the biggest. And it tells me 39 neighbors' weights is uniform. That means it doesn't matter much how far the neighbors are away. And this is what I put in here, train the whole thing, and well, we're done. And you can be pretty sure that this is, oops, oh, I have to zoom out again, sorry. That this is the best result you can get with k-nearest neighbor. Okay, try to remember the shape, because we will get way better. But the shape, like the form of the decision boundaries, how we call them, it will stay like this. Has anyone expected something like this? From the beginning? Yeah? I have not, but a lot of people have, so my visual system might be bad. So, no worries. So, next thing. Next thing is decision trees. And decision trees.
Can I quickly ask what is
always.
the difference between the test score and the table score?
Oh, in this case, yeah, very good question. I don't know, but we will, yes, we just check. So the test score is, no, the training score, I'm sorry, is 70%, which is not bad, but the test score is, holy goodness, how's that possible? There's always a little bit of randomness in this, so this catches me by surprise, to be honest. That means, which is very surprising, that means for the training data, the data that we know, it has a worse performance than for the data we don't know. This is suspicious. This, like, if in a real project, it's just 1%, so it could be like, because we don't have a lot of sample data, it could be just a little bit of random in this, but this would make me nervous if it was a real project. I can only explain by randomness, but this is typically something that never happens. But, or should not happen. But this means there's, just looking at the code to see if something of the code is wrong, but it looks okay.
But this data is prone to something like that.
Maybe, yes. Maybe,
It's over each other with different categories, and in the training set and in the test set, they are probably maybe not stacked at.
It's possible, yeah. And yes, good point. It's always like we just have to make it visible on the screen, I just selected 1,500 data points. This is typically, it's barely enough. So some people say you should not start below 5,000 samples per category, and you have 500. But if you have 5,000, it would take longer. Yeah, so, yeah, it's still like black magic to me, to be honest. Yeah, but good point. So now we know this doesn't overfit, but we only get 70%. Maybe not so bad. So decision trees, please, and always ask if there's something unclear. Maybe give me a second here. I'm looking for something else. What is it? Oh, I was looking for something like this. So a decision tree works like what you as a programmer, who's a programmer? You, yes. So what you might as a programmer write if your boss or PO comes up to you and tells you, I've analyzed this, we have certain rules for like how we make the split of the drivers, and this is what you would do by hand, using if-else, nested if-else blocks, quite a few of them, maybe 20. So your boss would fire you for this. But this is what the machine learns. So there's always a split, and it's always a split over a certain variable. And which variable it is, it depends on the settings that you make. But in this case, it says, we make the split. Well, let's scroll down so I can see the point. We make the split over the speed, and if it's below 146, then we go this way. And then we're done already, which is interesting. That means for all the cars, which is very surprising to me right now, for all the cars that are below 146 as a speed, the classification will be yellow. But on the other hand, we check, is the speed, this is too fast. I guess this decision tree must have been printed on kilometers per hour. Otherwise this is insane speed, right? And also this thing, and it makes sense. This as a German car, this is extremely slow. I'm not even sure if something like this exists. And if you drive an extremely slow car, you're a mediocre driver. I don't know why, but this is what the data set tells us. But then, again, there's a split. Again, over the same variable, there's a Gini cost or coefficient that I think we saw that in the keynote yesterday. I was very surprised to see this outside of machine learning, but the Gini coefficient tells us the impurity of the sample. In this case, it's 0 because it's just pure; it's all yellow. And in this case, it's well, you could interpret it as it's only 1/3 of it is correct. Well, yeah. And you want to get this down. In this case, you're perfect. Okay, this is what is learned, and that's enough of you. Sorry, that's enough of you. Sorry, no, it's not enough of you. For you, so enough for you to know. So you know there are splits, there's a depth in the tree. You have a certain set of samples that is in each node, and you can also configure something else in the decision tree, namely how many samples do I still have to have left in a node that's not pure to still split it. And these are exactly the parameters that you use to tweak such a decision tree to make it not overfit. So let's see. I think this is our first try. It looks like this. And as I said, these plots, you rarely get them in real life because you always have more than 2 variables. But in this case, you get it, but you see all these blocks. And these blocks, they are there because of the nature of decision trees. So you always have like these decisions, and each decision cuts a block into smaller blocks, and you see all this blocky thing here. This is very, very typical for a decision tree. And in this case, it's overfitting, so 96%. Overfitting score, it's very close to the k-nearest neighbor. And the test data, it's 60%. So it's also pretty bad. So now we changed the parameters, as I said, namely, I think I have to zoom in. Code. Oops, disappeared. We again search over the parameter. That means like how deep can the decision tree be? How many samples do I need at least in the leaf node? So, oh yeah, okay, yes, makes sense. And how many samples do I need at least to still make a split? And you see, that's quite a range. And it tries all these combinations, and again, it runs just 10 seconds. It tells me the maximum depth of the tree is just 6, which is really shallow. And then minimum leaf sample is 1, and the split is 5. Okay, that's interesting. You see, I have different variables here, or different values here, because the input data, I think it varies a little bit. So this should be deterministic as a search, but I think the input data is not always the same, so the way I pre-configured it is this, which is similar but not the same. So let's have a look. How well does it do? And this is how it looks like. It almost looks good, except for maybe this one and this one. The decision boundaries are smooth, but they still look like blocks. And you can see now, because the depth is just 6, the blocks get, well, in this case not. I'm a little bit surprised by this, but typically the blocks get bigger. I'm not quite sure where the lines come from, but it always changes a little bit. But typically you get bigger blocks, because you can't go down in the depth of the tree very far. So, this is test data. Again, the values, I keep forgetting this. This is 74, but the test data is 68. So we're getting this value up, but we're still pretty much overfitting. And this is also like, decision trees also are prone to overfitting. So what we do in the next thing here, that we train a lot of decision trees on always a sample of the, or just the fraction of the data, and we combine them back together. And this is called random forest. So a lot of them, we know each of them overfits, but at the end we average over all of them and get something that's hopefully better. And let's have a look at the graphs here. This is again non-regularized, very bad, but we're not at the end here. This test score is 63, so it's bad. But now we again making the grid search, but I think, no, wrong. So what we have is again the same variables as before, but we also say how many, how many decision trees do we want? Like how many decision trees do we want and to later combine to a whole thing? And we go between 3 and 20. And you can never be quite sure you're getting the best result, because in this case, it's also a deliberate choice to restrict this. And now I see this in my notes here. This takes too long, so I can't do this. Unfortunately, I can't do this. So what I do instead, I don't use like the brute force search, like the grid search, but a random search. That means it takes a certain amount of samples, in this part here, in our case 1,000, and it tries out 1,000 samples. It tries to find the best setting. Well, we could wait for the result, but I think it takes a long time. So we take the random forest classifier and always gives different answers. Let's see. So it tells us max depth is 19, 7 estimators, and then this is what I delivered before, which is, where's max depth? Which is very different. Look at this. Cool. So if you get very different results, it's very likely that you maybe should increase this number, like the number of iterations. But still, let's have a look. And again, we're just looking at the decision boundaries, and we are in block world again, and now you don't see the strange artifacts. You see this thing down here, which is strange enough, but this looks like, if I looked at this, I would say, this is probably not overfitting by much, because it has very clear boundaries. It has some holes, but not that many. So the test score is 70%, and the, let's see, oops. No, the test score is 70% and the training score is 73%. So overfits a little bit, but not very much. So let's see, shall we come to TensorFlow now? I guess so, because we have only a few time left. So there's support vector machines, which used to be like the hottest thing before deep learning. And I still like it. And I will show you the results, like the best results for support vector machines, to give you an impression how good they are. I like them very much. But they're not fancy. You can't go to customer and tell them we use support vector machines. No, really, they don't want it. They want the deep learning thing. Except for this, which is really strange. I haven't seen this before. Every time I run it, it looks a bit different. This looks really nice. So this is what we want to see. This is a little bit strange here, but then maybe it's due to the number of samples, but that's a pretty good result, just by looking at it. And I think the scores is, well, no, I don't think I read it. The score is 71% for test and 71% for training. So this is like probably as good as it gets. So there are two parameters that you can, again, tweak, which are a little bit hard to understand, but if you had more time, you go to this interactive thing and then you would understand. But now we're coming to deep neural networks, and they actually already need a proper GPU, need a proper GPU to run. And the GPU is a graphic card, more or less. So the graphic card that's in this system would do, but we're using the K80 from Google. So, zooming in again. That's how you import TensorFlow. So this is version 11, and then you can ask it, what kind of devices do you have present? And it tells us we have a GPU, yay. And if I had turned on the TPU option, we would have a TPU. And the training code would look a little bit different. Unfortunately, it's not the same. It's the same for GPU and CPU, but not for TPU. But anyway, so I think we can't go into the details of the neuron. And to be honest, you don't need to know, I would say. And we also, unfortunately, can't go into the details of the setup of a neural network, why it is the way it is, but we would just look at the setup, which is this. It looks a little bit more complicated than the others. So the others, they just look like they were often just one-liners. It's a sequential model. That means the data flows from input to output. It has two hidden layers. That means those are the layers of neurons that are in the middle, and this qualifies it as deep learning. So deep learning, more or less, to say it, is a marketing hype. So it's like, we use neural networks, but this time, so it failed in the 90s when I was studying computer science, but this time we use more hidden layers. And that makes it deeper, and now works. And that's the whole trick. That's why it's called, well, deep neural networks. A little bit disillusioning, but that's the way it is. And we have 500 neurons in each of the hidden layers. There's an activation function but this goes beyond what I can explain today, and then we tell it, give us a prediction for each of the three categories. And this is the number of parameters, which is also interesting. That means all of a sudden we have 500,000 parameters to train, and this works in iterations. And now we're in the area of minutes of training, which is very fast for neural networks, but typically not so fast. But let's see, what's interesting? What can I show you? So first I'll show you the results of this, which is 73% for training and 70% for test. And what's nice, because I can plot more, is like how it is training. So neural networks are trained in iterations, and with each iteration, oops, if you know what you're doing, you can plot the accuracy. The time? Okay. You can plot the accuracy, and you see this, wait, it's always hard if you stand so close to it. This line is, well, I didn't explain this properly, but you could read it as the test accuracy, and this dot thingy here is the training accuracy. There's more to it, but It doesn't matter much now. And you see from a certain point it doesn't change much, but you also see maybe a little bit that it diverts. You don't see it good here because of the scale, but it diverts the more you train. And this gives us certain ideas, and it also makes me pretty sure that we're overfitting. Just by looking at this. Maybe it's obvious, maybe not, but if it's not obvious, you will, if you look at a few of them, it will be obvious. And this is the plot, and it still has holes in it. And it looks a little bit fractured. So we know we can do better. And we apply a lot of strategies, which are really complex, to be honest, to fight overfitting. This is our new model. And just look at the size of the definition. We did a few things. Actually, I did everything I could. So probably too much, trying to show like how strong I am, but probably it was, maybe it was idiotic, I don't know. So, but the numbers of parameters also shrunk to just a little bit more than 10,000. I trained for less, and this is the time it takes for training, which is 40 seconds for just one training thing. But now, let's have a look at the results. So, for training data, almost 72%. For test data, around 70. Now look at this thing here. It looks much better. Well, for me it looks much better because I just look at this part of the plot. But now, maybe that's the last thing I can show you. How do you think will the plot look like? Like the decision boundaries, the red and then the green thingy. Similar. It does. So there's no surprise, unfortunately. It looks almost the same as the support vector machine thingy. And I spent a lot of time optimizing this, and the support vector machine thingy was grid search, put in the parameters. You always have to know which parameters to tune, but that's it. And this probably took me a few days to actually apply all the regularizations here, and you get more or less the same result. Like this, you know, Baba Papa? Anyone know Baba Papa? No. Baba Papa? No one? Yes, you know. That's Baba Mama or something, maybe. And it's the same result. So I think with this, I have to close. I tried to show that the different strategies have different upsides and downsides. And if you ask me which one to use as a default, I would use random forest because it often works just well. Or use it as a baseline. You make a very fast training using random forest, and then after that you have to be much better than random forest, or otherwise your approach doesn't make any sense, or not much. I think we had time for questions in between, but is there, we have, I think, 1 minute for, no? Okay, no questions? Are there questions? That's a question, yes. Please wait for the mic, because we have such a large audience.
So should I take away from this that neural nets are better applied to images?
Yes.
Things like that?
Absolutely. So if you wanted my advice, which I'm not sure if you want, but for like tabular data, neural networks often are not good, at least from my experience. But you have to use them if you want to apply them to images, if you want to apply them to sequences of text. But in this case, at least with this data, I had no advantages. Yes, this is only my opinion, and I know that there are other people who have other opinions. So take it with a grain of salt. Yeah.
So pretty much in all of them, we ended up with a training rate and a kind of validation rate of about 70%.
Yes.
And the only thing we were really using to work out whether it was good or bad seemed to be the visualization.
Yes.
So in high dimensional data, without the visualization,
Good.
why would you just stop at 1? Because you could probably save yourself 3 days.
Yes. So that's what I do. Yes. I've never done this on this data set using neural networks. This is just as an example, just as an experiment. I would actually have stopped at random forest, which I did for data set that was very similar to this. But typically, support vector machines give outstanding results, even with very little data. Certainly not little. Small data, I don't know. I'm German, sorry. If you don't have a lot of data, support vector machines give really good results. Yeah. And if you went into detail with this, you would understand why. And neural networks simply need a lot of data to be trained properly. I think that's it. Thanks a lot, and have a nice day.